how our solar system affects our climate. This is a graphic animation of the famous Shoemaker-Levy 9 comet when it made the fatal mistake of getting too close to Jupiter. Jupiter's powerful gravitational force heated up the comet until it exploded into 1,000 pieces. This is an artist's drawing of Enceladus, one of Saturn's many moons. Enceladus is thought to have a liquid water ocean beneath its icy cover. The ice and dust particle geysers are thought to be powered by gravitational heating as this moon travels its eccentric orbit. This all leads to my question. If the gravitational forces of Jupiter and Saturn are so powerful that they can heat up a comet until it explodes, or they can heat up a moon until liquid water geysers can be seen on its surface, in a place in the solar system where water should be frozen as hard as steel, what effects do the gravitational forces of the two biggest planets in our solar system have on our sun? Or asked another way, does our sun heat up when Jupiter and Saturn approach and then cool down as they move farther away? This image shows Jupiter at its perihelion, the point in its elliptical orbit that is closest to the sun. If we draw a line from Jupiter through the sun out to Jupiter's orbit on the other side, we will be at Jupiter's aphelion, the point furthest from the sun in Jupiter's orbit. This will tell us when Jupiter is closest to the sun and when it is farthest away. And this image shows Saturn at its perihelion. If we draw a line from Saturn through the sun out to Saturn's orbit on the other side, we will be at Saturn's aphelion. This will tell us when Saturn is closest to the sun and when it is farthest away. When we combine these two lines on one image, it gives us an easy-to-follow guideline about when it will be hot, warm, and cold. Approximately every 20 years, Jupiter overtakes Saturn, and they form a conjunction with the Sun. And every 60 years, the conjunction happens closest to the perihelions of Jupiter or Saturn. This is the point where these planets should exert the greatest tidal force against the Sun during that 60-year period. When a conjunction happens between the two perihelions, it will always be a hot 20-year period. And if the conjunction happens between the two aphelions, it will always be a cold 20-year period. All the other 20-year periods will be warm. If a conjunction happens between the two perihelions, the 60-year pattern will also be hot. This is where the great civilizations of the past 5,000 years have all started. If a conjunction happens between the two aphelions, it will be a cold 60-year pattern, and this will be where famines and crop failures destroy civilizations. Looking down on our solar system from a heliocentric viewpoint, we can observe Jupiter overtaking Saturn to form the three conjunctions that happen every 60 years. And every 60 years, one of these conjunctions happens closest to the perihelion of Jupiter or Saturn. This is the point where these planets should exert their greatest gravitational force against the Sun. If we continue forward with an additional 60-year period, we notice that the new period does not start over in the same place in the sky. This is because Jupiter takes 4/10 of a year longer to finish 5 orbits than it takes Saturn to finish 2 orbits. This precession effect makes this view look like a slow-moving counterclockwise clock. Notice that the year 2000 and the year 1940 conjunctions happen in the hot zone, which would tell us that this is where the hottest point in each 60-year cycle would take place. Using the same data but using a different way of viewing the data, this slide shows Jupiter held in place with the Sun and Saturn orbiting around Jupiter. This view is much easier to see the 20-year conjunctions without labeling them. This view will also tell us which 20-year conjunction was closest to the Sun without checking the data. We can continue to mark where the conjunctions occur, but as you can see, this is no longer necessary, since the conjunctions always occur at the tip of Saturn's loops. If we allow this process to continue, it will take Saturn about 1,000 years to form this pattern around Jupiter. Notice that the loops at the top come much closer to Jupiter than the loops at the bottom. The loops at the top that comes closest to Jupiter marks the warmest point in the 1,000-year pattern, the medieval warm period, and the loops at the bottom that peaks at the closest point farthest from Jupiter marks the coldest point during the Maunder minimum. Scientists have named these little ice ages and warm periods minimums and maximums because they refer to the amount of solar activity during these periods. This chart is from NOAA showing worldwide temperature increase since we began keeping track in 1900. The first arrow on the left shows the bottom of the last 60-year cycle in 1910. The next arrow pointing down shows the top of that cycle in 1940, approximately 1 degree Fahrenheit warmer than the 1910 bottom. The third arrow pointing up shows the start of the present 60-year cycle in 1970. This period also showed a 1 degree increase in temperature at the peak in 2000. And the final arrow shows the bottom of this 60-year cycle. The second chart shows 20-year conjunction peak numbers for the same period, with the numbers inverted for comparison purposes. When we combine the two charts, we see that they predict a strong drop in temperature during the next 20 years, just slightly warmer than the temperatures in the 1950s, 60s, and 70s. We do not have long-term data because world temperatures were not recorded before 1900. Scientists have tried using proxy data such as tree rings from all over the world or ocean deposits from all of the oceans. I find the results they are coming up with using proxy data to be subjective at best and mostly unreliable. This chart shows my calculations of the hottest year in each 1,000-year period. These hot years are 913 to 914 years apart, as we see on the next line. These should be near Saturn's perihelion, which is the most prosperous and successful time to be alive during the 1,000-year period. On this screen, I have assembled the largest empires of the last 5,000 years on a timeline starting with the Old Kingdom of Egypt during the time of the building of the Great Pyramids and ending with our own American empire. And on this screen, I have calculated where the warm and cold periods would occur during each of the last 5 climate cycles and where we are in our present 914-year climate cycle. When I combine these two charts, it should show us in what kind of climate period the great empires are most likely to develop. Here on this screen, we see that all the empires start when the weather begins to warm up, and they peak when the climate cycle reaches its warmest period. Our current climate cycle will not reach its warmest point for another 200 years. To summarize what we've talked about today, looking at the 6,000-year chart, we see that peak temperatures are dropping by about 1% every 1,000 years. You'll see this with the red circled numbers at the bottom of the chart. Looking at the current 1,000-year pattern, we will gradually warm up until the year 2238, near Saturn's perihelion. Looking at the 60-year patterns, the next pattern will be slightly warmer than this one, but before we get to that pattern, we will have to go through a 20 to 30-year cold period, like what we had during the 1950s, 60s, and 70s. The black circle at the right shows you where that cold place will be. In 2017, Jupiter will reach its aphelion, its greatest distance from the Sun. And in 2018, Saturn will reach its aphelion. This should make 2017 and 18 a very cold period compared to the warm weather we have had recently. In conclusion, our solar system is a giant thermostat and rheostat that gets warmer and brighter when the big planets approach the Sun, and colder and darker when the big planets move back from the Sun. We live on a planet that is warmed and cooled by this process, and we are powerless to do anything about it.